So far, when we've been talking about systems at equilibrium, we've just been kind of dealing with any particular type of chemical reaction. So when we have reactants that get changed into very distinct products. Now, there's a type of equilibrium that exists in solutions, and this is called solubility equilibrium. And when we are working with solubility equilibrium, we use something called the solubility product constant, which is basically its symbol is KSP right here. All right, so solubility product constant, or KSP, is basically a K equilibrium for a specific equilibrium when it has to do with solubility. Now, before we move even forward with working with KSP, let's just redefine what solubility is. So solubility, like we learned in previous chemistry, is how much solute will dissolve in a solvent under specific temperatures and pressure and all that stuff. But it's how much will dissolve. It's basically the maximum concentration. So how much of it will dissolve before you get excess solute in the solution. So there's a special case of equilibrium that occurs in a saturated solution where excess solute, so solid solute, is in equilibrium with its aqueous solution. So basically, this dynamic equilibrium it's an equilibrium that looks like this. It's when we have undissolved solid, so solid copper chloride here, in equilibrium with its dissolved ions. So it's an equilibrium between dissolved and undissolved solute. When we're dealing with an equilibrium between undissolved and dissolved solutes, we use KSP, solubility product constant. It's a value obtained from equilibrium law applied to saturated solution. So its formula is exactly the same as K equilibrium. Because we're dealing with solubility, it's temperature specific. Okay, because the amount of solute will change the amount of solute that dissolves will change depending on temperature. So KSP is temperature specific, which means when we state a KSP, we have to include what temperature it's at. So for example, the KSP of copper 2 chloride solid is 1.7 times 10 to the negative 7 at 25 degrees. As soon as you change the temperature, the KSP value is going to change. Just like the other K equilibriums we've been working with, it does not. The units vary, so we don't give it units. But there's a couple rules for our KSP. So it only works for ionic compounds with low solubility, because highly soluble substances do not form precipitates, and the solution will not form a solubility equilibrium. And the KSP value includes the concentration of the solid. So when we're thinking about our dynamic equilibrium up here, the KSP value includes this concentration of the solid. So we don't include it in our expression, and you'll see what I mean when we do an example. So I would pause and make sure you have this copied. All right, so when we are working with KSP, there are 4 types of calculations. One is calculating KSP using solubility. Another one is determining equilibrium concentration using KSP. And sometimes you'll see it referred to as calculating solubility using KSP. The third one is determining if we'll get a precipitate, and the fourth one is called a common ion effect. So in this video, we're going to work on or take a look at calculations number 1 and number 2. So our first type of calculation, we're going to calculate our KSP using solubility. And we want to calculate our KSP for magnesium fluoride if the solubility of magnesium fluoride solid is 0.00172 grams per 100 milliliters. So if we think back to grade 11, we learned that solubility is communicated in grams per 100 milliliters. So how much will dissolve in 100 milliliters of solution? So the first thing we have to do is we have to think about what is the equilibrium that's going to be occurring. We have the solid MgF2, and it's going to go in equilibrium with its ions. So if we remember, what happens to ionic compounds is it dissociates into its individual ions. So our equilibrium that's going to happen that we're applying KSP to looks like this. Magnesium fluoride solid in equilibrium with a magnesium ion and a fluorine ion. And I just want to point out to you that there is 2 fluorine ions here in the ionic compound, and so there has to be 2 fluorine ions right here in the equilibrium or when it dissociates. And we knew that already from when we were looking at how our ionic compounds dissolve last year. Now, in order for us to calculate KSP, we have to convert our solubility into concentration, because we know that equilibrium law, K equilibrium equals concentration of products over concentration of reactants. So we have to take our solubility and turn it into concentrations. So we're going to do that using our conversion factors. We're going to take our solubility, which is 0.00172 grams over 100 milliliters, and we have to convert it into moles per liter. So first thing we'll do is we'll convert our mils into liters, and we're going to use a conversion factor for that. So this is going to look like previous ways where we've converted our units. So we have milliliters, and we need to turn our unit into liters. So we're going to use a conversion factor that there is 1,000 milliliters in 1 liter. So if we do the math here, what we'll do is we would figure out how many grams are in 1 liter. But we need it in moles per liter. So now we're going to use our molar mass as a conversion factor to convert our grams into moles. And I already calculated it. I know that our conversion factor is 62.31 grams per mole. Now I have grams on the top in here, and I need to convert it into moles. So I'm going to put the 62.31 grams over 1 mole. So if I do my math, I punch this all into my calculator, I get 2.8 times 10 to the negative 4. And if we do a quick little unit check, we're going to see that we've actually converted our units properly, because this grams and this gram is going to cancel out. And come on, this milliliter, oh, that is not what I wanted. Come on. Did it even go to blue? The stylist is killing me here right now, guys. Okay. This milliliter, maybe go. There we go. And this milliliter cancel each other out, and we're only left with the units that we were looking for. Mole per liter. So that ends up being our units, mole per liter. All right, so we know our concentration of our magnesium fluoride, our solid. If we go back and we look at our dynamic equilibrium is magnesium fluoride is making a magnesium ion and 2 fluorine ions. So if we say that this is X, then a magnesium is also going to be X because it's 1 to 1. And our fluorine is going to be 2X. So we're going to say that this equals X up here. Okay. So technically, we don't worry about our... Oh, come on. Never mind. Okay. So we know that the solubility of magnesium fluoride is 2.8 times 10 to negative 4, and that equals X. So magnesium concentration, the concentration of the magnesium ion is going to equal X, which equals 2.8 times 10 to negative 4. And the fluorine ion concentration is going to equal 2X. So 2 times 2.8 times 10 to negative 4 mole per liter, and it ends up being 5.6 times 10 to negative 4 mole per liter. And then, so now you have the concentrations of your ions. So you've just calculated those. You can then just put them in a KSP. Now, remember a couple things with our KSP. It's basically just K equilibrium. It's just the equilibrium law expression, something we already know. But we don't put the solid underneath. So when we're calculating KSP, it's basically just this part that gets to come into the expression. So using our same rules, that 2 coefficient for the fluorine has to appear superscript by the fluorine ion. We sub in our values and we get an 8.8 equals 10 to the negative 11. Remember, we don't have any units, so we don't have to put anything in there. And then we can say we have a therefore statement. Therefore, the KSP for magnesium fluoride is 8.8 times 10 to negative 11. So all you are doing is calculating solubility. So molar solubility, moles per liter. And then you are figuring out how much of each ion would be dissolved based on how much solid you had and how it dissociates into our ions. And then you're putting that concentration, those concentration values into a KSP, or basically into an equilibrium law formula without the solid concentration. Okay, that's the big key here. So now let's look at another example, our second type. We're going to calculate solubility using KSP. And in our example, it says calculate molar solubility if KSP of zinc hydroxide is 7.7 times 10 to the 17. So we know that our equilibrium is our zinc hydroxide dissociating into zinc ion, 1 zinc ion, and 2 hydroxide ions. Okay. So we're going to take these values, and just like how we calculated K equilibrium in the past, we're going to use an ice table. Okay, so here's our ice table. We are putting dashes here for the solid because we don't care about the solid. The solid does not go in the KSP expression. There's zeros for initial concentrations of both ions because we don't have any to start. We're gaining plus X. We know the equilibrium is shifting this way because we are not starting with any ions. We're starting with a solid. The solid dissociates. At some point it stops dissociating, or at some point the dissociation and the recombining of ions starts being the same. That's the equilibrium. So when we're starting, though, our solid dissociates into the zinc ions and the hydroxide ions. So it's plus X and plus 2X for the hydroxide. So we know that at equilibrium is going to be X for zinc and 2X for hydroxide. So we put in our KSP expression. KSP is going to equal zinc, concentration of our zinc ion times concentration of our hydroxide ion squared, just like equilibrium law. And we sub in our values. So I'm going to show you this here. We're subbing in our KSP equals X for zinc and 2X squared for hydroxide. Do the math. We get something that looks like this, and we just follow it through like we've done before. And I'm showing you all of my steps here. We solve for X, and our X ends up being our molar solubility. So molar solubility, our X value, 2.7 times 10 to negative 6. That's what we're looking for. So X in a KSP is our molar solubility. So we're going to finish off with a therefore statement. Molar solubility of zinc hydroxide is 2.7 times 6 times 10 to negative 6 moles per liter. Okay, so those are the two types of KSP questions that we're going to look at. One is determining, calculating KSP, and the other one is calculating solubility using KSP. We'll look at the next couple types as we move through the rest of the week. Okay, so make sure you do some practice on this so you get pretty confident at working with our KSP.